Hello, everyone. Today, we're going to look through the chapter Acids, Bases, and Salts. So before we move into the chapter, let's look at this question that is given in the textbook. If someone in the family is suffering from a problem of acidity after overeating, which of the following would you suggest as a remedy? Lemon juice, vinegar, or baking soda solution? So it's quite clear that we would be checking out the option of baking soda solution, right? Why? Because as mentioned, we know that the problem is due to acidity, and baking soda solution is basic in nature. So we look at this phenomenon called neutralization, which is the ability of acid to nullify the effect of a base. It's known as neutralization. And since baking soda solution is basic in nature, we would be able to find relief when we take baking soda solution as a remedy against the problem of acidity. So now I want you to look into the question, what is neutralization? I want you to define it in your own words. As given in the textbook, it is the ability of acids and bases to nullify each other's effect. So before we go into the chapter, let's look at some important terms that you would be using throughout the chapter. So the first one is hygroscopic. Hygroscopic means tending to absorb moisture from the air. So these compounds such as honey, glycerin, ethanol, methanol, concentrated H2SO4, and concentrated NaOH, they usually tend to absorb moisture directly from the air. So they are known as hygroscopic. For example, you always store honey in closed bottles. That's because it is hygroscopic in nature. The next term is deliquescent. Deliquescent means these water-soluble salts, which on exposure to the atmosphere, they absorb moisture from the atmosphere to the extent that they dissolve in it. This is quite different from hygroscopic. They usually absorb moisture from the atmosphere to the extent that they even dissolve in it. For example, we have calcium chloride, magnesium chloride, and zinc chloride. The next term is efflorescence. It means the loss of water of crystallization from a hydrated salt to the atmosphere on exposure to air. For example, we have gypsum. The chemical formula is given, as you can see. Then we have effervescence, which is the fizz or bubbles formed on a liquid. For example, you have the soda, where you can see bubbles formed and you can see them moving upwards in those bottles. And then we have hydrated salts, which are crystalline salt molecules loosely bound to water molecules. So these salts have water molecules bound to these salt molecules, and they're known as hydrated salts. They're quite different. They're very different from anhydrous, which means these anhydrous salts usually contain no water. That is, there is no water molecules bound to these salt molecules. Now let us look at the difference between acids and bases. So acids usually produce H plus ions in water, and bases produce OH minus ions in water. Acids usually have a sour taste, whereas bases have bitter taste. For example, when you taste lemon juice, it tastes sour, right? Then we have the reaction of acids in contact with litmus paper. It changes blue litmus to red, and bases turn red litmus to blue. Acids are sticky to touch, and bases are slippery to touch. For example, when you touch soap, that they are basic in nature, and it is slippery to touch, right? And then we have acids, which are soluble in water. Bases are also soluble in water, but only some of them are soluble in water, and they're known as alkali. Now let us look at some sources in which you can find natural sources of acids. For example, lactic acid is found in cheese, yogurt, soy sauce, and pickled vegetables. Citric acid is found in citrus fruits like oranges, tomatoes, and pineapples. Oxalic acid is found in leafy green vegetables, beets, and tomatoes. And acetic acid is found in ketchup, mayonnaise, and mustard. Now let's look at the difference between strong acid and a weak acid. Strong acids are acids which dissolve or ionize completely in water. So they ionize in water to form H plus ions. So they release H plus ions. And some examples of strong acids include HCl, HNO3, H2SO4. And H2SO4, as you can see, it is a colorless acid. And strong acids are also known as inorganic acids or mineral acids. Then we have weak acids. Weak acids are acids which dissociate or ionize only partially in water, and they partially release H plus ions. For example, we have H2CO3, which is a weak acid, but it's not organic, it is inorganic acid. Then we have other weak acids such as citric acid, tartaric acids, lactic acid, malic acid, etc., which are organic acids. Now let us look at the difference between a strong base and a weak base. So strong bases are those that ionize completely in water to dissociate and form OH minus ions. For example, we have sodium hydroxide, potassium hydroxide, calcium hydroxide, and magnesium hydroxide. All of them are strong bases. Then we have calcium hydroxide and magnesium hydroxide, which are strong bases, but they are weak alkali. Then we have weak bases, which ionizes only partially in water to dissociate and release OH minus ions. For example, we have NH4OH and CuOH twice. Now let's look at what alkalis are. Alkalis are the bases that are soluble in water. For example, we have caustic soda, which is sodium hydroxide, milk of magnesia, which is magnesium hydroxide, and baking soda, which is sodium bicarbonate. So what are indicators? So you must have heard of this term indicators, which are usually used to indicate the presence of an acid or base. So the definition is that they are the substances which give different color in different medium and thus indicate the presence of acid or base in a solution. So we usually talk about the indicators which give a change in color when they try to indicate the presence of an acid or base. But there are also indicators which differ in the smell in the presence of acid or base, and they are called olfactory indicators, which we will come back to later. So indicators are of two types, natural indicators and synthetic indicators. For example, in natural indicators, we have litmus, and litmus in the presence of acid, it turns from blue to red, and bases turn red litmus into blue color. Then we have turmeric, which is another natural indicator. In the presence of acid, there is no change, whereas in the presence of base, it changes to reddish brown in color. For example, if you spill curry, which has turmeric, on a piece of cloth, it's initially yellow in color, but then when you try to wash it off with soap, on the presence of soap, it turns its color into reddish brown color, and that's because of the reaction of base with the presence of turmeric. So it indicates turmeric is usually essential in indicating the presence of a base, in which it turns its color to reddish brown. Then we have purple cabbage leaf and colored petals of some flowers such as hydrangea, petunia, and geranium. Then and in acids, it remains colorless, and in the presence of base, it turns pink in color. Then we have methyl orange, which is initially reddish orange in color. In the presence of acid, it turns red, and in the presence of base, it turns yellow. Now let us look at what litmus is. So litmus is a solution which is a purple dye that is extracted from lichen. And lichen is a plant that is belonging to the division Thallophyta. And this litmus is commonly used as an indicator. So when it is neither acidic or basic, its color is purple. So the original color of litmus is purple. Now let's come back to olfactory indicators. So olfactory indicators are the substances whose smell varies depending on whether it is mixed with an acid or basic solution. For example, in the presence of acids, there's usually no change in the smell. And in the presence of bases, the smell of these olfactory indicators vanishes. For example, we have onion and vanilla. Now let us look at some of the chemical properties of acids and bases. And in this, we're going to be discussing about acid or base in the presence of a metal or reacting with a metal. Then acid or bases reacting with a metal carbonate or a metal bicarbonate. Acids and bases reacting with each other, which as we have noticed before, which is the neutralization reaction. Then we have acids plus metal oxide, base plus non-metal oxide. And finally, we're going to look at the electrical conductivity of the solution of acidic and basic solutions. So these activities, activity 2.1 and 2.2, help you to learn about the reaction of indicators in the presence of acidic and basic solutions. So as we progress into the chapter, you will be able to identify these answers to how each of these samples would behave with each of these indicators, right? So moving on with the next activity, which is to test how acids and bases react with metals. So in this activity or in this experiment, we have 5 ml of dilute sulfuric acid in this test tube, and we're adding a few pieces of zinc granules to it. So basically, we're trying to react metals with the presence of a concentrated acid. So when we pass this delivery tube through a soap solution, we can see that there are bubbles emerging out of the soap solution. Due to this reaction, we have some bubbles emerging out, and these bubbles, when they come in contact with a burning candle, they usually burn with a pop sound. So why is that so? So as we can see, that acid, when they react with metal, they form salt and hydrogen. And these bubbles that emerge out of the soap solution are usually bubbles filled with hydrogen gas. So how do we know that it is hydrogen gas that is present inside? Because as these bubbles liberate out, and when we bring a flame close to it, in contact with it, it burns with a pop sound. That is because hydrogen is highly flammable. And that's how we get to know that these bubbles contain hydrogen gas. Weak acids usually do not dissociate quickly in water. And that's the reason we use a concentrated acid like sulfuric acid. So the reaction of weak acids with zinc is slower as compared to strong acids like HCl or H2SO4. That is, the gas formation is slower. So why are these bubbles formed? So usually when the hydrogen gas is passed through the soap solution, it does not get dissolved in the soap solution, and rather it tries to escape from the solution into the outer environment. And when it reaches the upper surface of the soap solution, it escapes as bubbles. So as it tries to escape as bubbles, these bubbles are formed because in the soap solution, there is comparatively less space compared to the surrounding air where the hydrogen gets more space to spread. And that's the reason why it tends to escape as bubbles. So the next reaction we're going to look at is base plus metal. So for this, we're going to do the experiment mentioned in activity 2.4, in which we're going to take a few pieces of granulated zinc metal in a test tube, and we're going to add 2 ml of sodium hydroxide solution, and then we're going to warm the contents. So when you do this, the reaction that takes place is that as we add NaOH to zinc, we get this salt called sodium zincate, and there is hydrogen gas that is liberated. So as you can see, when bases react with metals, we get the formation of salt and hydrogen gas is liberated, similar to acids reacting with metal. But you need to note that only amphoteric metals like zinc and aluminium react with bases. Now let us look at the reaction of acids with metal carbonates or metal bicarbonates. So for this, we're going to perform the experiment given in activity 2.5, and we're going to take two test tubes, and we're going to label one of them as A and the other one as B. So in the first one, we're going to take about 0.5 grams of sodium carbonate, and in the other one, we're going to take sodium hydrogen carbonate, which is sodium bicarbonate, and each of these we're going to add 2 ml of dilute HCl. So basically, we're adding an acid to one test tube with a metal carbonate and the other test tube with a metal bicarbonate. So what do you observe? From this delivery tube, as we pass the delivery tube into a test tube containing calcium hydroxide solution, we can see that the gas evolved from the reaction gives a precipitate in calcium hydroxide solution in the test tube. So that precipitate is calcium carbonate. So as we can see, the reason why we form calcium carbonate in the test tube when we pass the gas that is obtained from this reaction through lime water is because of the liberation of the gas carbon dioxide. So we can finalize that as we react an acid with metal carbonates or metal hydrogen carbonates, we get salt, water, and carbon dioxide. And do note that bases do not react with metal carbonates or metal bicarbonates. So the occurring reactions in the activity can be written as this is for test tube A and this is for test tube B. So this is the reason why when we pass the carbon dioxide gas that is evolved through the reaction, when we pass it through lime water, we receive calcium carbonate, which is noted as a white precipitate. But when we pass excess carbon dioxide into the same solution, the calcium carbonate solution, we find out that the solution, which was milky in the beginning, the milkiness disappears when you pass excess carbon dioxide into the same solution because the solution changes from calcium carbonate to calcium bicarbonate, which is soluble in water. And since it dissolves in water, it is no longer a precipitate. And because of that, the milkiness disappears and you see more of like a clear solution. So here are different forms of calcium carbonate. This is for general knowledge. So you have eggshells that contain calcium carbonate. Then we have limestones, chalk, and marble. The next reaction that we're going to look at is the reaction of acid and base with each other. So this reaction, as we have noticed before, it is called the neutralization reaction. So for this, we're going to perform the experiment given in activity 2.6, in which we're going to take NaOH solution in a test tube and add 2 drops of phenolphthalein solution. So as you can see, there's a base in the presence of phenolphthalein solution, which is an indicator. It turns pink in color. And then we're going to this NaOH solution, we're going to add HCl solution. So the thing that we're trying to do here is noticing any color change for the reaction mixture. So I want you to answer this question. Once the neutralization reaction happens, what is a color change? Since we added phenolphthalein to the NaOH solution, it was pink initially. And after we add HCl solution, there is a neutralization reaction happening. And I want you to answer what kind of color change could you expect? So moving on to the reaction, this is a chemical equation as given below. So as you can see, the base sodium hydroxide reacting with a HCl gives us a salt NaCl or sodium chloride, which is common salt, and gives out water. So this is known as the neutralization reaction. The next reaction that we're going to look at is acid plus metal oxide. So for this, we are performing this experiment. in which we're taking a small amount of copper oxide in a beaker. So copper oxide is a metal oxide, and we're adding dilute hydrochloric acid, and we're slowly stirring it. So what happens to the color of the solution? So the observation here is that initially the copper oxide is black, and once it reacts with HCl, it turns about blue-green in color. Why does it turn blue-green? Because of the formation of calcium chloride. Sorry, copper chloride, copper 2 chloride in the reaction. So initially, CuO is black, but it reacts with HCl to form CuCl2, which turns it blue-green in color. So CuCl2 is the salt that is formed as a result of the reaction, and we also get water. So this is quite similar to the neutralization reaction in which we add an acid and base, and it gives us salt and water. So you might be provided with a question that says, prove that metallic oxides are basic in nature. So this experiment could be used to prove that metallic oxides are basic in nature because they react in a similar way as acids and bases react with each other. And similarly, non-metallic oxides can be said that they're acidic in nature. Similar to the way that we proved metallic oxides are said to be basic oxides, we can also prove in a similar way that non-metallic oxides are acidic in nature because of the similar kind of reaction that the base reacts with an acid to form salt and water. So as an example, you can provide this reaction, which is sodium hydroxide reacting with carbon dioxide, which is a non-metallic oxide, to form a salt, sodium carbonate, and water. So the next thing that we're going to look at is if all the compounds containing hydrogen are acidic. For example, you have compounds such as glucose and alcohol, which also contain hydrogen. So we're going to test if these compounds also are acidic. So for that, we're going to perform this experiment in activity 2.8, in which we're going to take solutions of glucose, alcohol, hydrochloric acids, and sulfuric acid. So as you already know, hydrochloric acid and sulfuric acid are acids, as we have seen before. Now we're going to test if glucose and alcohol can be considered as acids. So now we're creating a simple circuit over here, and we're fixing 2 nails on a cork, as you can see, and we're placing it in a 100 ml beaker, and we're filling it with the solution, with each of these solutions, glucose, alcohol, hydrochloric acid, and sulfuric acid. And when we connect these wires to a 6-volt battery and a bulb, we see that the observations made are, in the presence of glucose or alcohol, the bulb doesn't glow, which means it does not conduct electricity. Whereas in the presence of hydrochloric acid and sulfuric acid, the bulb glows. That is, it conducts electricity. So why is that so? This is because acids ionize in water to release H plus ions that conduct electricity. So as we have seen in the presence of HCl or sulfuric acid, these acids release H plus ions in water, and these H plus ions are necessary to conduct electricity. These are the things that conduct electricity and make the bulb glow. Whereas in the presence of glucose or alcohol, they do not conduct electricity because they do not dissociate in the solution to produce H plus ions. Hence, we can conclude that glucose and alcohol cannot be considered as acids. Also note that all acids containing H plus ions conduct electricity, whether they are mineral or organic, but not all compounds containing hydrogen are acidic. And we can also note that acids, bases, and salts increase the electrical conductivity of water because of the release of ions. Next, we're going to see what happens to an acid or base in an aqueous solution. So for this, we're going to perform this experiment, activity 2.9. in which we're going to take 1 gram of solid NaCl in a clean and dry test tube, and we're going to add concentrated sulfuric acid to it. So what do you notice? Of course, there's a gas that is evolving from the test tube, right? So we're going to test this gas with dry and wet blue litmus paper. So what changes do you observe in the litmus paper when we test it with first with dry litmus paper and with wet blue litmus paper? So the observations made are when this HCl gas is tested with dry blue litmus paper, it does not change color. All right. And in the second observation, we can see that when HCl is tested with wet blue litmus paper, it changes blue litmus to red. The reason is because there are no H plus ions that are released in the dry HCl and in the aqueous solution of HCl, which means when this HCl gas, which is dry initially, is tested with wet blue litmus paper, because of the contact of water, it becomes aqueous, due to which H plus ions are released and it changes color to red, which means the H plus ions are the ones that are responsible for the acidic nature of acids such as HCl, whereas when it is rather dry, when H plus ions are not released, they usually do not tend to show acidic properties. Similarly, bases in aqueous solutions, they release OH minus ions, and red litmus paper works on this OH minus ions and turns into blue. Do note that weak bases do not completely dissociate in water. So you can also note from here that concentrated H2SO4 or sulfuric acid is a non-volatile acid, the acid that we've used in the experiment. It has a high boiling point. That means it can be used to prepare the acids that are volatile, such as HCl and HNO3, so that a dry gas is formed. And we require a dry gas over here so that we can test it easily with dry and wet blue litmus paper in order to get accurate results. So now we're going to look at what happens when we try to dilute an acid or base in water. So I want you to consider these 3 questions. The first question is that, is the process of dilution an exothermic reaction or an endothermic reaction? The second question is, why should acid be added to water and not vice versa? You must have heard usually that we say we always add acid to water and not water to acid. Why is that so? And the third question is, what is dilution? I want you to consider this and I want you to be able to define dilution in your own words. So for this, we're going to perform the experiment activity 2.10, and we're going to take a 10 ml water in a beaker, and we're going to add a few drops of concentrated sulfuric acid to it and swirl the beaker slowly. And you can notice that there is a change in temperature, which means the beaker slowly starts heating up. This is because this process is highly exothermic and heat is liberated when you try to dilute an acid in water. Also, you can remember that acids should be added to water and not water to acid. You can remember it as A to W, which means like A comes first alphabetically. So do always remember that acids must be all added to water and never water to acid. This is because if water is added to a concentrated acid, since the reaction is highly exothermic, the heat generated may cause the mixture to splash out and even cause burns. And also the glass container may break due to excessive local heating. So that's why you can see these kind of warning signs in the beakers that can contain concentrated acids and bases. And also, during the process of dilution, the concentration of H plus or OH minus ions, whether it is an acid or base, during the process of dilution, the concentration of these ions reduces per unit volume. This process is called dilution, and then the acid or base is said to be diluted. Now we're going to test the strength of an acid or base. So looking at what is a universal indicator. So I want you to answer this question. The answer is given as a universal indicator is a mixture of several indicators, and this universal indicator shows different colors at different concentrations of hydrogen ions in a solution. And we usually use this using a pH scale. So pH scale is used for measuring this hydrogen ion concentration in a solution and to test whether the solution is acidic or basic. So generally, this pH paper is usually the paper impregnated with the universal indicator, and it is used for measuring pH, which is used to test the strength of an acid or base. So pH stands for P standing for potens, which is power in German, and H for hydrogen, which is basically the power of hydrogen or the concentration of hydrogen ions. So here are some important pH values that you could remember. For example, gastric juice has a pH of about 1.2, lemon juice has about 2.2, tooth decay, anything less than 5.5 results in tooth decay. Acid rain is less than 5.6. Ideal soil pH is from 5.5 to 7.5. Human blood is slightly alkaline. That means it is a slightly higher number than the neutral pH, which is 7.35 to 7.45. Distilled water has a pH of 7.4. Human body 7.0 to 7.8. Milk of magnesia is 10. And sodium hydroxide solution, which is a really strong base, it is about 14. And pH scale ranges from 0 to 14. So as you can see, this is a picture of the pH scale. And below the value of 7, the acidic nature increases. And above the value of 7, which is neutral, the basic nature increases, denoted by the increase and decrease in hydrogen ions. So the strength of these acids and bases depends on the number of H plus ions and OH minus ions produced respectively. For example, if we take hydrochloric acid and acetic acid of the same concentration, say 1 molar, as you already know that hydrochloric acid is a stronger acid than acetic acid. So if we take the same concentration of both of these acids, say 1 molar, then these produce different amounts of hydrogen ions. So it is important to note that concentration is not equal to the strength of the acid. Acids that give rise to more H plus ions are said to be strong acids, whereas acids that give less H plus ions are said to be weak acids. So usually concentration refers to the amount of acid dissolved in a given volume of solution, but it does not account for the degree of ionization or the dissociation of the acid molecules. So comparing acid strength versus concentration, usually in strong acids, such as hydrochloric acids, they completely dissociate in water. This means that every molecule of HCl releases one H plus ion into the solution. So for a 1 mole solution of HCl, the concentration of H plus ions is also 1 mole because all HCl molecules dissociate fully. Whereas in case of weak acids like acetic acids, they only partially dissolve in water because they are weak acids. So this means that only a fraction of acetic acid molecules release H plus ions into the solution, even if you take 1 mole solution of acetic acid. So that's it for today. Stay tuned for part 2.